everybody, my name is Georgy and I'm a PhD student at the University of Copenhagen at a place called Center for Star and Planet Formation, and it's all at the Globe Institute. So today what I'm going to be... we don't know this, we don't know the age of the Earth, so that's the big spoiler today. But I'm going to be talking about how we're trying to figure it out, and what we already know, and mostly I'm going to be talking about what we don't know actually. But yeah, and one of the many sciences that's trying to figure it out is called Cosmochemistry, and that's the topic of my PhD. Cosmochemistry as in space, cosmos, and mostly it's about taking some samples. Usually it's meteorites, like we try to get samples from asteroids and Mars and Moon and sometimes Earth even, and mostly we do it with meteorites. Sometimes if we get lucky and enough funding and enough, I don't know, everything, then sometimes we get samples delivered by some missions, but PhD students don't get to work with them anyway. And then we have the samples, and then we work in the lab trying to get some chemical information about those samples, and then we use this information to get some information about history of the solar system. And so if I want to figure out the age of the Earth, what's like the first most obvious way to do this, to try to do this? I guess it's just look for old things here on our planet. Yeah, and such thing exists in Australia, in Western Australia, in a place called Jack Hills, and they have rocks with a bunch of zircons. Zircon is a mineral. It's you can guess it involves zirconium in there. It's a silicate of zirconium, and so this is mineral. It's not that big. It's 100 micrometers. So like this whole thing would be like millimeter long for up until here somewhere. And for example, this particular one is 4,113,000,000 years old. MA is Latin for million years. So yeah, so this one, for example, is 4 and something billion years old. But how do we get this age? How do we know the age of this particular zircon? The thing is, zirconium here has very similar chemical properties to a bunch of chemical elements just in general in this corner. And this corner, this corner includes also this, and this is actinides, and one of them is uranium. I mean, all of them are radioactive, but uranium is not radioactive enough to still be around after the formation of the solar system. So we have uranium, and when we have radioactive decay, one chemical element transforms into another chemical element that's slightly lighter. Typically it's heavy chemical element that transforms into another lighter chemical element, and the difference in the mass is released via energy. So yeah, and uranium transforms into lead. Where is it? Oh my god. Yeah, Pb. Lead here. And lead doesn't have anything in common with zirconium in terms of chemical properties. So there is, it is silicate of zirconium, so there is a little bit of the similar in chemical properties uranium, but no lead. So if we do chemical analysis of this one crystal, we're going to see some lead in there. And because radioactive decay happens with a very specific and very easy law over time, we can actually, based on chemical composition, tell the age of this crystal. And it has been done for a bunch of, by bunch I mean 251, I think more, but this particular study did it on this one, for a bunch of zircons from there. And as you can see, their ages are quite diverse, and most of them have the ages of like 4.1 billion years old. Some of them go even as old as 4.4. So yeah, but how much informative this is this about the age of the planet? Oh, did you hear me before this? Right? Because I just remember that they told me to keep it closer to my mouth. Yeah, so what I was talking? Yeah, so how informative it is about the age of the planet? Because this is just this is a crystal somewhere in Australia. I mean, it's not a planet. It's not representative of a planet, definitely. And what are zircons? So on the left you can see a granite, and it's a rock that's usually formed when we have somewhere, we have volcanic activity, we have a volcano, and under that volcano we have a bunch of magma in a magma chamber, and that's liquid magma is what fueling the volcanic activity. But at some point when volcanic activity stops, the magma chamber also cools down, solidifies, crystallizes, and from some small portion of this magma we have crystals of zircon as well, somewhere in there. And then, so those are the rocks that we see actually at Jack Hills. And those are not granites, even though they look as old and as red, I guess. Those rocks are actually, so if you look at, so this is a pebble, this is a pebble, this is a pebble, there is a bunch of black, I don't know, dirt in there, okay, sediment, something. This rock was formed as a sediment in a river. So first we had some volcanic activity, so first the earth formed, and that's what we're trying to date. Then there was volcanic activity, then this volcanic activity stopped, then the magma chamber below the volcanoes solidified, then this magma chamber somehow got exposed onto Earth's surface, and then there was a river which was flowing through that leftover volcano, and then in that river, somewhere closer to the delta of the river or something like this, there was a bunch of pebbles and sand that included some of those zircons from those granites, and that's why we have such a big range in there. And also such a big range of ages of those zircons, because it's actually not from one granite, it's from a bunch of different places. And also, as you can see, so these red spots, this is, okay, we call it weathering, but rust, it's rust. So this rock had seen some chemical reactions after being formed back then when it was formed. I think the rock itself, so the zircons are super old, and the rock itself is also super old, but the rock itself is, like, the river was there, I think 3-point-something billion years old. So like quite a while after the volcanic activity we're talking about. So it's seen has some chemical reactions because it's altered, there is some rust in there, there is something going on, which means if we're trying to get some chronological information from our chemical compositions, how much can we trust it? So again, on our range, so yeah, okay, because we get so much ages in this here, okay, probably this is actually informative. This, like, there was some volcanic activity on Earth already at this time, but we don't know if this is just another zircon from another volcano, or is it altered because of weird chemistry that's happening on the Earth's surface or something like this. So it's hard to tell really. Yeah, but to sum up this first step, so this is 3.8 million years ago, billion years ago, 4.4 billion years ago, and a bit before, because that's where we're going to go after this. And oldest zircons on Earth are somewhere here, probably everywhere, but definitely somewhere here. Probably all of this range actually. So we know that Earth was around before that time already. Something. So where do we go next after this? What we can try to do is try to find something else in the solar system because the whole problem with Earth for cosmochemists, I mean, we cosmochemists, we like pristine old things and primordial and something not altered. What the problem with Earth for us, if you're trying to study the history of the solar system, is that Earth is active. There is volcanoes, plate tectonics, rivers, trees, ants, penguins, humans. So yeah, basically, if we're trying to get an age of anything here on Earth, we're going to date this penguin or volcano. We're not going to date the whole planet. It's hard. So we can try to find something not as geologically active another place. And yeah, one of the places we can try is the moon, because we know that Earth and moon, it's a planet and a satellite, so they probably share some formation history somehow together. So it's actually a related body, celestial body to our planet. So getting the age of the moon is going to be actually informative here. And how do we do that? If you see, so those black things are dark, okay, not black and white, but dark gray and not as dark gray. So dark gray things are huge lava fields, so there was a volcanic activity there. But those brighter things, as you can see, so those are called lunar highlands. And as you can see, they have a bunch of craters in there. And usually we think that craters form on planets because meteorites fall on them, and we usually think that meteorites fall roughly uniformly over time. So basically, the more craters, the older the thing is. So the surface. So this surface is very old because it has a lot of craters. And also, we've seen some rocks from there, so we've seen them under microscope. And so, I've said this too early. So how did the moon form? We think, oh my god, yeah, this button. Yeah, we think that moon formed by something called giant impact. So there was two planets, one of them was proto-Earth, and then the other one, which we call Theia, and they collided, and then from the leftover material around, from this thing, at some point later, moon formation happened from leftover material of this collision. And when this happens, it all gets very hot. So we get a thing called global magma ocean. And so it's all molten. There is basically most of the moon is molten. We don't know how deep it goes, but probably deep enough that it's actually global magma ocean. And when it's molten, it's very hot, it starts to cool down eventually. And when it cools down, it starts to crystallize. And some of the crystals that grow there, they actually don't drown, they float. They float, and they also form rocks that look exactly like those ones, the one we see there. So we think that this white lunar highland thing is a primordial crust that formed as basically like a floating crust on the lunar magma ocean. And this whole thing, from the collision to the solidification, happens very fast. So getting actually the age of this is going to be a way better proxy for the age of the moon than our proxy with zircons for the Earth. Okay, and so a lot of people did this and they got different answers, which span over more than 100 million years of range. So, and we know that what we think is, like here we think it's not a big range, here we think that most people are just wrong, but we don't know who of those people are wrong. So yeah, again, we just have a range. But still, that range is smaller now, and we know that if it's giant impact, that the Earth was already around somewhere before this. So we basically know that at the latest, the Earth must have been around by this time, which is, again, a lot of information. Oh my god, did I hit this again? It's okay, yeah, okay, thank you. Yeah, okay, so what's the next step? So we have like, how it's called? Upper limit? No, lower limit for the age of the Earth. But let's try to get upper limit. So maybe we're going to end up with an interval of ages where the Earth could have formed. And for that we need this, because we think that the Sun formed the first in the whole solar system. But in Cosmochemistry, so I showed you the lab, and basically we can get a lot of information out of a sample we have in the lab. And getting a sample of a hot ball of plasma that self-gravitates and floats in space is very hard. There was even a space mission that tried to collect some material from it, like from the solar wind. But it's really not a lot of material to do kind of analysis we do, and also this whole thing crashed into desert, so half of the material was lost due to contamination in the desert. But still, there was a lot of good science out of it, but we cannot do ages with this. Yes, so let's talk about how we think stars form then. Stars form in giant molecular clouds. We call them molecular clouds because they have molecules apparently. What they also have, so it's basically a lot of dust and gas. And stars form in those clouds in thousands, like a lot of them. And it's all very chaotic, and when the protostar forms, it accretes, it consumes a lot of material from around, and when it does so, it gets way hotter and it shines way brighter than normal main sequence star does, like our Sun now. So we know that in the beginning of the existence of the Sun, there was a short period of time when Sun was way brighter and it was way hotter in general in the solar system. And Now we're going to talk about meteorites. So this is a meteorite, and when we look into meteorites, they have, so there are two big types of meteorites, and here we don't care about meteorites that are piece of a planet, piece of a volcano from Mars or something like this. Here, so this kind of meteorite we call a primitive meteorite, and it's basically a pile of dust from whatever was left after planet formation. So just, yeah, literally just a pile of dust, space dust, that was left after stars and planets formed in our neighborhood. One star, okay. Yeah, and so in those meteorites, in some of them we find those white things. And those white things are called refractory inclusions. Refractory means it's very hard to melt and even more so to evaporate. And they also called calcium aluminium, sounds so American, aluminium rich inclusions. Because they have a lot of calcium and aluminum, and if we look at those in the microscope, we see that they, judging from their structure, they formed from condensation from a gas. So there was a short period of time when the sun was very hot, and now we also see very rare inclusions that condensated from gas of calcium and aluminum. So it must be related, and indeed, so if we get ages of them, this is so those ages are very identical, so we get like we can get a lot of ages and they're all going to be almost the same. So it was a very short period of time. We're talking about, I mean, compared to 4.5 billion years ago, we're talking about tens or maybe hundreds of thousands of years, and that's it. So it's very short period of time by this in this astronomical scale. And all of those inclusions formed in very short period of time, which we know very precisely. It's 4,567,300,000 years ago, I think, according to Copenhagen. There are other people, but according to Copenhagen people, it's this. Yeah, so now we know that the Earth must have formed somewhere between this, which is now we have an interval of 100 million years or something like this, slightly more, which is already great. But maybe we can get even slightly better. How long am I talking? Perfect. Maybe we can get even slightly better. And for that we need to think, because we figured out that we cannot basically measure the age of the Earth anyway, but maybe we can try to estimate how long does it take to make a planet. And it all starts in a thing that looks like this, in radio. Okay, not in radio, I think it's far infrared or microwaves. In some kind of non-visible range it looks like this. And this is called protoplanetary disk. So after this chaotic and turbulent time of thousands of stars just forming together in a giant molecular cloud, next step is that our stars gets finally somewhat isolated, and they have a leftover of this disk of dust and gas around them. And we know that planet formation starts here, starts at this step, because we already see the main explanation for having rings and stuff in those disks is that we have forming planets there. So we think that planets form ultimately from this dust, and it all starts at this stage. And we also know kind of that this period is roughly 3 or 5 million years long in general. So it's, yeah. But to get from dust, so this is dust. I think this is supposed to be 10 micrometers. So it's tiny space dust. To get to planets, we need to cross, I think it's 13 orders of magnitude difference from dust to planets, and so it's a lot. We need to grow our solid particles in the disk, in the solar system, by a lot to get to planets. And while we have some idea how we grow from dust to asteroid-sized bodies, basically happens if we have enough dust just close to each other, then they start to gravitationally attract each other and just collapse into an asteroid. But how do we get from asteroids to planets is really a big question. And yeah, and we have some ideas how it happens, but they differ and they have different very different implications for how long it takes to make a planet. So one of the models is classical model. it's also called collisional growth, where we have a bunch of asteroids, and when there's a lot of asteroids, they sometimes collide with each other, and sometimes they stay together after the collision, and so we get a bigger asteroid. And then when it's a bigger asteroid, it's actually a little bit higher chance for it to stay together after another collision, because it's bigger and more gravitation. So this way we can get some planets, but this takes a while. So this can take up to 100 million years or even more. We don't know exactly, but it's long. And then there is another rapid growth model. So if a planet, if we already have some kind of protoplanet or small planet or big asteroid or something like this, while we still have this short-lived 3 million years disk of dust around the star, if we already have something heavy enough in this disk to just be gravitationally dominant in some area, then it starts just attracting the dust from the disk, and this can happen very fast. We can grow big planets very fast. And we know that gas giant planets form this way, because that's the only way they can still be, because once this dust is gone, so is the gas in the disk. And for Jupiter we need gas. So we know that they form fast, and that's the only way to make them fast. But we don't know this about the Earth, unfortunately. We don't know if the Earth and in general terrestrial planets, they grow slowly or quickly, and yeah. We have scientific community still not agreed on this matter. But to summarize what I just said, so we have the oldest things on Earth, somewhere here in this big range. Then we have the Moon that must have formed after the Earth, according to the giant planet formation theory, which is the only theory that actually explains at least half of the evidence. Doesn't explain all the evidence, unfortunately, as well. Then we have Sun, and we know that Earth must have formed somewhere between Sun and the Moon. And it could be fast if it's fast, and could be slow if it's slow. Yep. So to summarize, how do we know the age of the Earth? Is actually not quite badly. We barely know it. But that's what I'm working on. So specifically, our research group in the University of Copenhagen, that's what we do mostly. Is we try to get some meteorites, try to get some data about the chemical composition, and then because in those two different planet formation models we have different. So it's either asteroids or dust, and we try to figure out from meteorites what are the building blocks of the terrestrial planets, and then maybe we can tell a bit more about actually formation conditions and time scales. Thank you.
To ask, you talked about the Moon earlier and showed us the craters and so on. As well as I could see, there were far less craters in the part of the Moon where there was volcanic activity.
Yeah.
Why is that?
Because it happened. So when the Moon formed, first it was what we think, if there was global magma ocean. First it was all covered with this white highland terrain, and then at some places a bit later there was volcanic activity.
Okay, so that was afterwards.
Yeah,
okay.
Yeah.
Cool. Thank you.
If it was before, then we would have been dating this thing to get the age. Yeah. Thank you. Another questions? Or other questions? Yeah.
The bartender has a question.
Oh, okay, yeah.
How do we know that asteroids fall universally on the surface of the Moon?
Mostly.
Can you please repeat?
Yeah, so the question was, how do we know that, because I said that this is quite important for dating the surfaces of the planets with craters, how do we know that asteroids and meteorites actually fall uniformly over time? So, we know this mostly from the fact that I don't do this personally, so I kind of know it. So I think mostly from the fact that it all doesn't violate each other. When we use this as an assumption, the results we get are not contradicting to each other. And then also, so once we got Apollo missions there, they sampled different places with different crater densities, and this whole thing with it was anchored in some actual ages that we knew with the numbers, and it all looked. So all the evidence we have is that it uniformly. There is one time in one period in time when we think it might have peaked, and it was around, so 4.5 billion years solar system formation, and then planet formation, and then in the end of the planet formation we think it might have been actually more collisions than before that, but then after this period it was anyway declining uniformly. But with this period with this peak period, yeah, but it might have been one peak, but we don't know really yet. Thank you. Are there? Yeah.
When you get a sample in your lab, can you maybe describe what you do with it?
Yeah, can try.
What was the question?
Yeah, so just in general, what do I actually do with the samples in the lab? So we get usually, so those beakers are like, so I usually work with iron meteorites, which means that we have plenty of material that we like most people work with smaller samples, especially people who do ages, because they work with lead, and there is like so few lead in the solar system, and uranium, so they work with tiny samples. I work with huge samples, and by huge samples I mean I have in my sample, so I study nickel isotopes, and I usually, after this whole thing, I have 100 micrograms of nickel or something like this. That's a lot. That's the size of a pile, like small clump of dust, but it's a lot by our measures. Yeah, so usually we get like a sample, maybe several milliliters of a sample that's digested, dissolved in the acid. So this is a meteorite, liquid meteorite, because it's in the nitric and chloridic acid, this black thing. There is like roughly, I don't know, 10 milliliters of it, and it was before that it was like maybe 100 milligrams or 200 milligrams of a meteorite. So we get those samples, and then we do this. This is called column chemistry, because it's column and it's chemistry. And so again, I work with nickel isotopes, so what I do is I put my sample in solution in there, and then there is weird organic chemistry happening that makes red complexes with nickel that's stuck in this white resin, and I wash off all the other elements. So this is iron from my iron meteorites, and also all the other elements of sulfur and stuff like this in this iron meteorite. I care about this bit. Then I take this bit, I change the pH, I wash off this bit, then I do another chemistry to clean for other elements, so we repeat similar procedures, maybe depending on the element, several times. And then in the end we get one purified chemical element from our meteorite, and we do what is called mass spectrometry to measure its isotope composition. And then we use this isotope composition to either study precisely conditions of chemical reactions or make ages, or me specifically, I use them as I make a bunch of corrections, basically remove all the axes from my data, like remove so many dimensions from my data that like as possible. And then I get left with isotopic anomalies that we use as a fingerprint or DNA for building blocks of planets. Yeah. I hope that was explanatory enough. Thank you. Are there any other questions?
No more? So
oh yeah, there was one there.
Okay.
Yeah.
So how do you collect those old samples? Is there like hotspots on Earth that you know, or you just randomly sample some places?
So I personally just go to the Geological Museum. That's where my office is, and yeah, that's it. That's how I get the samples. They have collection. But people who do this, yes. So it's either falls that are observed, which happens rarely, or it's places. It's not hotspots as in where more meteorites fall or something like this. It's hotspots where meteorites get concentrated by geological processes, and also hotspots where it's easy to notice. So it's usually deserts, either ice deserts, and specifically places where ice goes up. So that means that all the meteorites that are in the ice are getting exposed, and I mean meteorites don't melt, ice does melt, so there is more and more meteorites, and also black meteorites, really easy to spot on the white ice, I guess kind of easy. I mean they probably not that easy actually, but easier than in the forest.